Welcome to my virtual classroom, the new style of learning which you may be familiar with. Here we learn chemistry for higher secondary classes. The classroom offers you a set of video classes on each chapter. We start with the basic concepts of chemistry, the first unit of class 11 chemistry. Since animations speak louder than words, I have included a lot of animations in these video classes. But a warning, animations never represent the real situation. It only helps you to understand the concepts more clearly. By the way, I am Dr. Suresh Matthew, a retired professor in chemistry. The purpose of my channel, Chemistry Master, is to upload video classes related to NEET, JEE Main and Advanced, KEAM, CUET, and other similar competitive examinations. This is part 2 of the set of video classes on the chapter Basic Concepts of Chemistry. It is a continuation of part 1 where we learned about precision and accuracy in measurements. The remaining parts of this chapter will be uploaded soon. If you like the video, please subscribe my channel and forward to others. Significant figures. As we saw earlier, every experimental measurement has some amount of uncertainty associated with it because of the limitation of measuring instrument and the skill of the person making the measurement. The uncertainty in experimental or calculated value is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus one which is estimated or uncertain. Now let us take an example. Suppose that I want to measure the weight of this small piece of stone. And for that, first I use a platform balance. Its accuracy is only 0.1 gram. That means the minimum weight we can measure using this balance is 0.1 gram. And this is a glass dish. We cannot place the stone directly onto the platform. It will spoil the balance. So first we place the glass dish. It weighs 6.2 grams. We can eliminate the mass of this glass dish by pressing the tare button. Now the weight is 0 gram. We place the stone piece in the glass dish and the weight shown is 5.6 gram. Since the accuracy of the balance is 0.1 gram, the weight shown is greater than 5.5 gram but less than 5.7 gram. And the best estimate is 5.6 gram. Now I repeat the weighing using another platform balance. And this one is more accurate than the first one. That means we can measure a minimum of 0.1 gram using this one. Now I place the stone here and the weight shown is 5.62 gram. Now going back to the first weighing, this 5 is certain because here also it is correct. Now the 6 is uncertain because there is another digit beyond this 6. That means the second weight is higher than the first weight by 0.02 gram. So we say that digit 6 is uncertain. Significant figures are meaningful digits which are known with certainty plus 1 which is estimated or uncertain. Meaningful digit means, suppose instead of 5 it is 0, we neglect it. It is meaningless. If it is 0.6, we do not count this. So the number of significant figures here is 2. Suppose that I am using a third balance. That also is a platform balance, but in this case it is more accurate than the first two. A minimum of 0.001 gram can be measured using this. Now you place the stone here. So the weight shown is 5.624 gram. Now coming back to the second weight, it is 5.62. Now we can say that 5 and 6 are certain. So in the second measurement, 5 and 6 are certain, but the digit 2 is uncertain because beyond 2 there is one more digit. So therefore the number of significant figures are meaningful digits which are known with certainty plus 1 which is estimated or uncertain. So this 2 is an estimated value. So the number of significant figures is 3. We now use a more accurate balance, and that is known as an analytical balance. We use this balance very often in our laboratory, and the accuracy is 0.001 gram. We can measure a minimum of this much. And the way we place the stone in this balance, and the weight is shown is 5.6245 gram. That is 5.6245 gram. Coming back to the third weight, and in this case 5, 6 and 2 are certain. But digit 4 is uncertain because there is one more digit beyond that. So 4 is uncertain or estimated. So the number of significant figures are meaningful digits which are known with certainty plus 1 which is estimated or uncertain. So in the third way, the number of significant figures is 4. Similarly, in this case, in the fourth way, the digits 5, 6, 2 and 4 are certain. And 5 is uncertain because if you have a more accurate balance, there may be digits beyond this 5. So in this case, the number of significant figures is 5. As we move from left to right, the number of significant figures increases from 2 to 5. Thus, the number of significant figures in a measured quantity gives an indication of the capabilities of the measuring device and the precision of the measurement. We have seen that measured quantities involve uncertain digits, but numbers obtained by counting or from definitions are exact numbers. They are known to be absolutely accurate. For example, the number of students in a classroom can be counted, and there is no doubt about the number of students. Similarly, a dozen eggs is defined as exactly 12 eggs, no more, no less. One dozen is equal to 12.0000. Infinite number of 0 can be added. So an exact number may be thought of as containing an infinite number of significant figures. There are certain rules for determining the number of significant figures. We need not learn it by heart. By doing certain examples, you can easily grasp those rules. First one, all non-zero digits are significant. Example, 285 centimeter. And in 285 centimeter, all the numbers are non-zero digits. So 3 significant figures. Now 0.25 ml. So this 0 is not significant. These 2 digits are significant. So therefore there are 2 significant figures. Second rule, zeros preceding to first non-zero digit are not significant. Such a zero indicate the position of the decimal point. For example, 0.03 gram has only one significant figure. These two zeros are not significant. And it shows only the position of the decimal point. Similarly here, these 3 zeros are not significant. And therefore it has only 2 significant figures. Third rule, zeros between two non-zero digits are significant. For example, this measurement 2.005 gram. And now these two zeros are within two non-zero digits. So therefore these two zeros are also significant. Hence, for this quantity, the total number of significant figures is 4. Now zeros at the end or right of a number are significant, provided they are on the right side of the decimal point. For example, 0.200 gram. And in this case, these two zeros are significant because they are towards the right of the decimal place point. Now, this quantity has three significant figures. But if there is no decimal point, the terminal zeros are not significant. For example, 100 gram. And this has only one significant figure, and these two zeros are not significant. But if you write it as 100.0 gram, and the zero towards the right of the decimal place is significant, therefore these two zeros are also significant. So altogether there will be 4 significant figures. Such numbers are better represented in scientific notation. 100 gram can be represented as 1 into 10 raised to 2 gram. In that case, there is only one significant figure. Now we can write it as 1.0 into 10 raised to 2 gram. So when you write it like that, this 0 also is significant. 2 significant figures are there. Now if you write it as 1.00 into 10 raised to 2 gram, there will be 3 significant figures. Counting the numbers of objects, for example, 2 balls or 20x, have infinite significant figures, as these are exact numbers and can be represented by writing infinite number of zeros after placing a decimal. That is 2 equals 2.00, etc. or 20 equals 20.00, etc. In numbers written in scientific notation, all digits are significant. For example, 4.01 into 10 raised to 2 has 3 significant figures, and 8.256 into 10 raised to minus 3 has 4 significant figures. Now consider a general example, 0.005003600. This zero is not significant. The reason is that zero is used for a decorative purpose. So just to show that the number does not start with a decimal. Now, these two zeros are also not significant because these two zeros are used only to locate the decimal place. Now, these 3 digits are significant because they are non-zero integers. Now, these two zeros are significant because they are zeros between non-zero digits or non-zero numbers. The last two zeros are also significant here because the zeros are at the end of a number to the right of the decimal point. So these zeros are towards the right of the decimal point and at the end of the number. So altogether, this will have 1, 2, 3, 4, 5, 6, 7. 7 significant figures. Let us work out some examples. Example 1. The quantity is 98.62 gram. And all are non-zero digits. So all the 4 digits are significant. So for this number, there are 4 significant figures. Example 2. 200 ml. Now these two zeros are not significant, that comes towards the end of the number. So therefore, this number has only one significant figure. Now here, this 0 is only for decorative purpose, and these two zeros determine the position of the decimal point. So therefore only these two digits are significant. So this has two significant figures. Now for the example, 9.02.10 gram. Now this 0 is in between two non-zero digits, so this 0 is significant. And this 0 also is significant because it comes after the decimal place. So altogether there will be 1, 2, 3, 4, 5. 5 significant figures for this number. Now 6.32 into 10 raised to 4 gram. Now this is a scientific notation, and here we have to consider these three digits, and these three digits are significant. So therefore there will be three significant figures. Now 200.0 gram. Now these two zeros are significant because this 0 is significant, and that comes to us the right of the decimal place. So therefore total number of significant figures will be 4. Now 0.1357, and this 0 is not significant. So therefore 1357 are significant. So 4 significant figures are there. Now 6.200 gram. These three zeros are significant because that zeros comes to us right to the decimal place. Totally there will be 1, 2, 3, 4, 5 significant figures for this quantity. Now in 6.02 into 10 raised to 23 atoms. And here it is a counting number. So therefore this will have infinite number of significant figures. Example 10, 400x, that also is a counting number. So it will have infinite number of significant figures. Very often we need to round off certain numbers or measurements. We can use certain rules for rounding off numerical results. If the rightmost digit to be removed is more than 5. Once again, if the rightmost digit to be removed is more than 5, the preceding number is increased by 1. If the rightmost digit to be removed is more than 5, the preceding number, that is number towards the left, is increased by 1. For example, 1.386. So we have to drop 6. So therefore 6 is greater than 5. So the preceding number is 8. It will increase by 1. So we round off this number to 1.39. If the rightmost digit to be removed is less than 5, then the preceding number is not changed. For example, 4.334, and if we have to drop 4, then the result will be rounded to 4.33 because the number to be removed is less than 5. Now, if the rightmost digit to be removed is 5, so if the rightmost digit to be removed is 5, then the preceding number is changed if it is an even number. But it is increased by 1 if it is an odd number. Once again, if the rightmost digit to be removed is 5, then the preceding number is not changed. It remains as such if it is an even number. That is, the number to be retained is an even number. But it is increased by 1 if it is an odd number. For example, 6.35. So we have to drop 5. Now 3 is odd. Therefore, this is rounded to 6.4. So 3 increased by 1. And if it is 6.25, now 2 is even and it is rounded off to 6.2 because the number to be retained is even. Here the number to be retained is odd. Let us consider some examples. Round off the following measured values to 4 significant figures. First example, 3984.6 gram. And this measured value has 5 significant figures. We have to round off it to 4 significant figures. So the last digit to be retained is 4 and the digit to be dropped is 6 and it is greater than 5. So the last digit increases by 1 unit. The round off value will be 3895 gram. 4 significant figures. Second example, 422.04 gram. Here also there are 5 significant figures. We have to reduce it to 4 significant figures. The last digit to be retained is 0 and the digit to be dropped is 4 and that is less than 5. So the last digit remains the same. So the round off value will be 422.0 gram. And here again there are 4 significant figures. Third example, 4854.5 gram. The last digit to be retained is 4 and the digit to be retained is now equal to 5. Since the last digit to be retained is even, it remains as such. Therefore, the round off value is 4854 gram and 4 significant figures. Another example is 3985.5 gram. And there are 5 significant figures. So the last digit to be retained is 5 and the digit to be dropped is also 5. Since the last digit to retain is odd, it increases by 1. So the round off value will be 3986 gram. That is 4 significant figures. Another example is 33,900 gram. And here there are only 3 significant figures. We have to write it in 4 significant figures. Therefore, we must use the scientific notation. So we move the decimal place to 4 places towards left. So it is 3.390 into 10 raised to 4. There are 4 significant figures. This 0 is significant. Another example is 5.0472 into 10 raised to minus 4 mole. There are 5 significant figures. So the last digit to be retained is 7 and digit to be dropped is 2. So the last digit remains the same. So the round off value will be 5.047 to 10 raised to minus 4 mole. 4 significant figures are there. Now let us use the significant figures in numerical calculations. First we consider addition and subtraction. When we add or subtract numbers, we should round the result to the same number of decimal places as the number with the least number of decimal places. So in addition and subtraction, we consider the decimal places of the values. That is the least precise value in terms of addition and subtraction. Consider this measured value 1.0056 gram and there are 4 decimal places. Second value 2.32 gram, 2 decimal places. Third value 4.5 gram, only 1 decimal place. Now we add these quantities. The result is 7.8256 gram. Now we have to consider the least precise value, that is having the least number of decimal place. So the result should be in one decimal place. So we have to, the last digit to be retained is 8 and a digit to be dropped is 2. So the last digit remains the same. Final value should be 7.8 gram. Now let us consider subtraction. 584 gram, no decimal place, minus 526.24 gram, two decimal places. So the result is 57.76 gram. And here this number has no decimal. So the answer also should not be having decimal places, or it should contain only ones. So the last digit to be retained is 7 and the digit to be dropped also is 7. So the last digit increases by 1. So therefore the final result is written as 58 gram. Next is multiplication and division. When we multiply or divide numbers, we should round the result to the same number of digits as the number with the least number of significant figures. That is, the least precise value in terms of multiplication and division. Consider this multiplication: 15.65 centimeter, 14.85 centimeter, and the result is 1173.632625 centimeter cube. So that is an volume measurement. So it has four significant figures, and this has four significant, but here we have only three significant figures. So therefore the result must be of three significant figures. The last digit to be retained is 7. We have to write this in the scientific notation. So 1.17 into 10 raised to 3 centimeter. Now consider division. 426.46 gram divided by 482 ml. The result is 0.8848 gram per ml. Now this number has only three significant figures. So the result also must have three significant figures. So the last digit to retain is 4 and the digit to be dropped is 8. So the last digit increases by 1 unit. So therefore the final result will be 0.885 gram per ml. This is because 5 significant figures by 3 significant figures, the result must be in 3 significant figures. Dimensional analysis. While doing calculations, very often we need to convert units from one system to another. The method used to accomplish this is called dimensional analysis. It provides a systematic way to convert units from one system to another. For example, meters to feet, kilograms to pounds, centimeter to meter, centimeter to angstrom, etc. In dimensional analysis, we first construct unit factors from any two terms that describe the same or equivalent amounts of whatever we may consider. For example, 1 meter is equal to 100 centimeter. So these two are equivalent amounts, 1 meter and 100 centimeter. Now we divide both sides of this equation by 1 meter. That is 1 meter by 1 meter, 100 centimeter by 1 meter. Meter and meter cancels. Therefore, 1 is equal to 100 centimeter by 1 meter. And this is the unit factor since the numerator and denominator describe the same distance. Therefore, the multiplication by this factor is same as multiplication by 1. Similarly, if we divide the first equation by 100 centimeter, we get 1 meter by 100 centimeter, 100 centimeter by 100 centimeter, centimeter cancels. That is 1 meter by 100 centimeter is equal to 1. And this also is a unit factor, and it is a reciprocal of the first. Consider some examples. Suppose we need to convert 3 meter to centimeter. For that, multiply 3 meter by the first unit factor. That is 3 meter is equal to 3 meter into 100 centimeter by 1 meter. So meter and meter get cancelled. So the answer will be 300 centimeter. To convert 400 centimeter to meter, multiply by the second unit factor. 400 centimeter and 400 centimeter into 1 meter by 100 centimeter. So we have to cancel centimeter here. So therefore the result is 400 by 100, that is 4 meter. Another example, and that is an example for volume conversion. A bottle contains 3 liters of milk. Express the volume in meter cube. And we know 1 liter is equal to 1000 centimeter cube. And 1 meter is 100 centimeter. And from the second equation, we construct the unit factor. We divide this equation both sides by 100 centimeter. 1 meter by 100 centimeter equal to 1. But here it is centimeter cube. So we need cube of this unit factor. 1 centimeter by 100 centimeter cube equal to 1. The whole raised to 3. That is 1 meter cube by 10 raised to 6 centimeter cube is equal to 1. And this is 10 raised to 2. And that is equal to 2 into 3, 6. That is 10 raised to 6. Volume of milk is 3 liter. That is 3 into 1000 centimeter cube. So 3 into 1000 centimeter cube into this unit factor. 1 meter cube by 10 raised to 6 centimeter cube. So the centimeter cube and the centimeter cube get cancelled. And therefore the result become, this is 10 raised to 6, this is 10 raised to 3. So 10 raised to 3 here. When it goes to the numerator, it becomes 10 raised to minus 3. So the final result will be 3 into 10 raised to minus 3 meter cube. Another example. A sample of gold has mass 0.23 milligram. What is its mass in kilogram? And we know 1 gram is equal to 1000 milligram and 1 kilogram is equal to 1000 gram. So we must use two unit factors. One to convert milligram to gram and then gram to kilogram. So we divide this equation by 1000 milligram. 1 milligram by 1000 milligram. So 1000 milligram by 1000 milligram equal to 1. And here we divide by 1000 gram. 1 kilogram by 1000 gram equal to 1. 1000 gram by 1000 gram. So the mass is 0.234 milligram. So 0.234 milligram into the first conversion factor, unit factor, it converts milligram to gram. So 1 by 1000 milligram. If you multiply it again by the second unit factor, it converts gram to kilogram. So therefore, milligram and milligram get cancelled. Then in the second multiplication, gram and gram get cancelled. And what remain is kilogram. So the final result will be 0.234 into 10 raised to minus 6 kilogram. 10 raised to 3 into 10 raised to 3. When it comes to comes to the numerator, it becomes 10 raised to minus 6. Writing in scientific notation, we move the decimal place one place towards right. So 2.34 into 10 raised to minus 7. The exponent decreases by 1. Example 4. A common unit of energy is erg. Convert 3.74 into 10 raised to minus 2 here to SI units of energy, that is joules and kilojoules. 1 erg is exactly 1 into 10 raised to minus 7 joule. So the equations are 1 erg is equal to 1 into 10 raised to minus 7 joule and 1 kilojoule is equal to 1000 joule. So we divide the first equation by 1 erg. 1 erg by 1 erg. 1 into 10 raised to minus 7 joule by 1 erg equal to 1. So that is the first unit factor. Now the second one, 1 kilojoules by 1000 joule, 1000 joule, 1000 joule equal to 1. And this is the second unit factor. Now the amount is 3.74 into 10 raised to minus 2 erg into the first unit factor. It converts erg to joule. Erg and erg get cancelled. So what we get is 3.74 into 10 raised to minus 9. Minus 7 into minus 2, 10 raised to minus 7, minus 9 joule. Now we have to convert this into kilojoule. So 3.74 into 10 raised to minus 9 joule into the second unit factor, 1 kilojoules by 1000 joule, and that is equal to 3.74 into 10 raised to minus 12. This is 10 raised to 3. When it goes to the numerator, it becomes 10 raised to minus 3. Example 5. Convert 400 picometer to meter, centimeter, and angstrom. These are the relations. 1 picometer is equal to 10 raised to minus 12 meter. 1 meter is equal to 10 raised to 2 centimeter. And 1 angstrom is equal to 10 raised to minus 8 centimeter. So the required unit factors are, we divide this equation by 1 picometer. That is 10 raised to minus 12 meter by 1 picometer is equal to 1. And here we divide by 1 meter. 10 raised to 2 centimeter by 1 meter is equal to 1. And we divide by 10 raised to minus 8 centimeter. 1 angstrom by 10 raised to minus 8 centimeter is equal to 1. Now, the value is 400 picometer. First, we convert it to meter. So, we use this conversion unit factor, that is 400 picometer into 10 raised to minus 12 meter by 1 picometer. Picometer and picometer get cancelled. So the result is 4 into 10 raised to minus 10 meter. Now we convert it to centimeter. For that we use this unit factor. 4 into 10 raised to minus 10 meter into 10 raised to 2 centimeter by 1 meter. So this meter and meter get cancelled. So the result is 4 into 10 raised to minus 8 centimeter. Now it should be converted to angstrom. 4 into 10 raised to minus 8 centimeter into the third unit factor, 1 angstrom by 10 raised to minus 8 centimeter, and centimeter and centimeter get cancelled. The result is 4 angstrom. Example 6. The radius of silver atom is 1.44 angstrom. Express the radius in picometer and centimeter. So the relations are 1 picometer is 10 raised to minus 12 meter. 1 angstrom is equal to 10 raised to minus 10 meter. In centimeter, it is 10 raised to minus 8. 1 meter is equal to 10 raised to 2 centimeter. First, we construct the unit factors. 10 raised to minus 10 meter by 1 angstrom is equal to 1. 1 picometer by 10 raised to minus 12 meter equal to 1. 10 raised to 2 centimeter by 1 meter is equal to 1. 1.44 angstrom into 10 raised to minus 10 meter by 1 angstrom. So the angstrom and angstrom get cancelled. So 1.44 into 10 raised to minus 8, 10 meter. Now the second conversion, 1.44 into 10 raised to minus 10 meter into 1 picometer by 10 raised to minus 12 meter. So meter and meter get cancelled. We get the result in picometer. 1.44 into 10 raised to 2 picometer. That is 1.144 picometer. We have to convert it into centimeter. So this value, this is in picometer. So we convert this into 1.44 into 10 raised to minus 10 meter. So we multiply by this unit factor, 10 raised to 2 centimeter by 1 meter, and that is 1.44 into 10 raised to minus 8 centimeter. Let us work out some multiple choice questions and short answer type questions related to the topics we have studied so far. Question 1. Which of the following statements about a compound is incorrect? A molecule of a compound has atoms of different elements. A compound cannot be separated into its constituent elements by physical methods of separation. A compound retains the physical properties of its constituent elements. The ratio of atoms of different elements in a compound is fixed. Remember, we have to choose the incorrect statement. So, first one, a molecule of a compound has atoms of different elements. And that is a correct statement. So, that is not our answer. A compound cannot be separated into constituent elements by physical methods of separation. That also is correct. We cannot use physical methods to separate the constituents of a compound. So that also not our answer. A compound retains the physical properties of its constituent elements. Compound has properties different from its constituent elements. So this statement is wrong. So this is our answer. Yes, that is the correct answer. The ratio of atoms of different elements in a compound is fixed. That also is a correct statement, and which is not our answer. Question 2. The measured value 0.012456 gram, when written in scientific notation with the three significant figures, will be 1, 2, 3, 4. So the scientific notation is n into 10 raised to n. So n is the exponent and capital N is a digit term. So we have to move the decimal point 2 places towards right. And we have to write it in three significant figures. So therefore, the last digit to be retained will be 4 and a digit to be dropped is 5. Since it is even, the last digit remains the same. So the correct option will be 1.24 into 10 raised to minus 2. That's the correct answer. Question 3. A measured temperature on Fahrenheit scale is 200 degree Fahrenheit. What will this reading be on Celsius scale? Option 1, option 2, option 3, option 4. So we can use the conversion equation. Degree Fahrenheit is equal to 9 by 5 into amount in degrees Celsius plus 32. So we need Celsius. So degree Celsius is amount in Fahrenheit minus 32 into 5 by 9. So 200 degree Fahrenheit
minus 32 into 5 by 9, and that is equal to 93.33. So the correct option will be option 3. When the absolute temperature is 400 Kelvin, the corresponding Fahrenheit temperature will be option 1, option 2, option 3, and option 4. So the conversion relations are degree Fahrenheit is equal to 9 by 5 into degrees Celsius plus 32, and Kelvin is equal to degrees Celsius plus 273. So first we convert this to degrees Celsius. So degrees Celsius is equal to Kelvin minus 273. That is 400 minus 273. That is equal to 127 degrees Celsius. Now we convert it into Fahrenheit. That is 9 by 5, 127 degrees Celsius plus 32. So the value is 260.6 degree Fahrenheit. So correct option is option 4. Question 5. Cesium atoms are largest naturally occurring atoms. The radius of a cesium atom is 2.65 angstrom. How many cesium atoms would have to be laid side by side to give a row of cesium atoms 1 inch long? Assume that atoms are spherical. Given that 1 inch is equal to 2.54 centimeter and a 1 angstrom is equal to 10 raised to minus 8 centimeter. Option 1, option 2, option 3, and option 4. So here we have to consider a row of cesium atoms. So we can consider this as a row of cesium atoms, and suppose that this distance is 1 inch. So therefore, if we know the diameter of one cesium atom in inch, we can calculate the number of cesium atoms in this distance. So here the radius is given as 2.65 angstrom. So we can find out diameter, and that also will be in angstrom. So we have to convert it into centimeter and then to inch. First we have to find out the unit factors. So diameter of a cesium atom is 2.65 into 2, that is 5.30 angstrom. 1 angstrom is equal to 10 raised to minus 8 centimeter. So therefore we divide by 1 angstrom. So the unit factor will be 10 raised to minus 8 centimeter by 1 angstrom, that is equal to 1. Now 1 inch is equal to 2.54 centimeter. So we divide 1 inch by 2.54, and 2.54 centimeter by 2.54 centimeter is equal to 1. So this is the second unit factor. 5.3 angstrom into 10 raised to 8 centimeter by 1 angstrom. Angstrom and angstrom cancels. So it is 5.30 into 10 raised to minus 8 centimeter. Now we convert it into inch. So 5.30 into 10 raised to minus 8 centimeter into 1 inch by 2.54, that is 2.09 into 10 raised to minus 8 inch. We can do it in a single step. So therefore the diameter of a cesium atom is 2.09 into 10 raised to minus 8 inch. So therefore number of cesium atoms in 1 inch will be 1 inch divided by 2.09 into 10 raised to minus 8 inch. That is 0.478 into 10 raised to 8. Write it in scientific notation. We move the decimal place one place to its right. So the exponent decreases by 1. So it is 4.78 into 10 raised to 7 atoms. So the answer will be 4.
Two students performed the same experiment separately, and each one of them recorded two readings of mass, which are given below. The correct reading of mass is 3.0 gram. On the basis of given data, mark the correct option out of the following statements. Student A and B readings, first reading, second reading. 3.01, 2.99, 3.05, 2.95. Options 1, 2, 3, and 4. And let us take the average value of these two readings for both the students separately. Student A 3.01 plus 2.99 by 2 equal to 3.0 gram. It is exactly equal to the correct mass. The difference between his values is 3.01 minus 2.99 equal to 0.02 gram only. So his measurement is precise and accurate. Now student B, the average is 3.05 plus 2.95 by 2. That again is 3.0 gram. So the value is accurate, but the difference between his values is 3.05 minus 2.95 equal to 0.1. And that is much higher compared to student A. So his measurement is accurate but not precise. So the correct answer is the results of student A are both precise and accurate. That is the correct answer. Question 7. The result of the following addition after rounding off will be. So we have three quantities 2.5 gram, 25 gram, 150.05 gram. Option 1, option 2, option 3, option 4. And now let us add these quantities. So the sum will be for 425.55 gram. Now, the least precise value here is 25, no decimal place. So the answer should also be written without decimal place. So the last digit to be retained is 5, and the digit to be dropped also is 5. Since the last digit to be retained is odd, this increases by 1. So the answer should be 426. So 426 gram, that is the correct answer. Question 8. Arrange the following measured values in the increasing order of precision. 200 gram, 1.08, 0.0043, 250 gram, 246 gram. Option 1, option 2, and option 4. The precision refers to the number of significant figures or the number of digits after the decimal point in a measured value. 1.082 has 4 significant figures but only 3 digits after the decimal point. On the other hand, 0.0043 has only 2 significant figures but 5 digits after the decimal point. So in this case, 1.082 is less precise compared to 0.0043. And we know this is the least precise value. And next comes 250, only 2 significant figures. Then 246, 3 significant figures. So in these cases, we count the significant figures. Now come to these two decimal places, and 0.0043 has 5 decimal places, while here it is only 3 decimal places. So this is the correct order of precision. So the answer should be this one. Question 9. Using the rules for significant figures, the correct answer for the expression
will be option 1, option 2, option 3, option 4. The answer is 0.00561374. And now this quantity has 4 significant figures. Here it is 3 and here it is 4. So in multiplication and division, we consider the number of significant figures. And this is the least precise value. So therefore the answer must have only 3 significant figures. And the last digit to be dropped is less than 5. So the value will be 0.00561 and the answer must be option 2. Question 10. Given the measured value is 171 centimeter, 0.171 centimeter, 0.0171 centimeter, the number of significant figures for the three measured values are 1, 3, 4 and 5 respectively, 3, 3 and 4 respectively, 3, 4 and 5 respectively, 3, 3 and 3 respectively. And here we have three significant figures, 171. And here also we have 3, 0.0. This 0 is not significant. And here these two zeros are not significant. Therefore, 171, that is three significant figures. So all the three quantities possess three significant figures. So the answer should be 3, 3 and 3 respectively. Question 11. The number of significant figures to be present in the answer of the following calculation. Option 1, option 2, option 3 and option 4. This also is division. Division and multiplication we consider the least precise, which is the value having the least number of significant figures. In here, this quantity has only two significant figures. So the answer should be expressed in two significant figures. So option 2 is the correct answer. Question 12, an assertion reason type question. Assertion, significant figures for 0.200 gram is 3, whereas for 200 gram it is 1. Reason, 0 at the end or right of a number are significant provided they are not on the right side of the decimal point. Option 1, both A and R are true, but R is the correct explanation of A. Option 2, option 3 and option 4. So here the reason is wrong. 0 at the end or right of a number are significant provided they are not on the right side. So if they are significant only if they are on the right side of the decimal place. So reason is wrong. So the answer is A is true. Significant figures for 0.200 gram is 3 because these two zeros are significant. They are to the right of the decimal place. And here this is the zeros after a non-zero digit. So these two zeros are non-significant. So therefore 200 has only one significant figure. Assertion is correct, but reason is wrong. So therefore the correct answer is option 3. Question 13. Match the number of significant figures with the corresponding measured or counted values. So measured values and the number of significant figures. Then options are option 1, option 2, option 3 and option 4. Come to measured value A, 0.00246 gram. And all the three zeros are not significant. So this quantity has three significant figures. So look for three significant figures. So the second option is three significant figure. So we can connect this to this one. So A can be connected to 2. Now measured value B, 2.002. Since these two zeros are within two non-zero digits, so these two zeros are significant. So total number of significant figures will be 4. So we can connect this to 4 significant figures. Now, measured values. This is a counted number, well, counting number 6.02 into 10 raised to 5 atoms. Counting numbers have infinite number of significant figures. So look for infinite. So this is infinite. So we connect B to C to 5. Then 25,000 liter. And these three zeros are not significant. So therefore the number of significant figures will be 2. So here it is 2 significant figures. So we connect D to 3. D to 3. Now this one is 5 into 10 raised to minus 12 meter. This is the scientific notation, and this has only one significant figure. So E can be connected to 4. Therefore the correct option should be option 4. The SI unit of density is option 1, option 2, option 4. SI unit is kilogram per meter cube. So option 3 is the correct answer. The absolute zero temperature is 0 Kelvin. In Celsius unit, which one of the following is the absolute zero temperature? Option 1, option 2, option 3, option 4. And that is minus 273.15 degrees Celsius. Very often we write it as minus 273. Next we consider numerical questions. Question 1. Find the mass of a rectangular piece of copper of 24.4 centimeter into 11.4 centimeter into 7.9 centimeter. Given that the density of copper is 8.92 gram per centimeter cube. So first we have to find out the volume, and then we can calculate mass from the given density. We know density is equal to mass by volume. Therefore, mass is equal to density into volume. Therefore, mass is equal to 8.92 gram per centimeter cube, that is the density, into 24.4 centimeter into 11.4 centimeter into 7.9, and this will be the volume. The answer is 19,601.379 gram. Now, in this calculation, the least precise value will be 7.9, and that is, it is having only two significant figures. And in multiplication, we consider the significant figures, number of significant figures. So the answer should be expressed in the same significant figures as that of this one. So we have to express this in two significant figures. So the digit to be retained is 9, and the digit to be dropped is 6. So 9 increased by 1. So in order to keep the same value, we must express in scientific notation. It is 1.9601. So when 6 we are dropping 6, so 9 increases by 1. So therefore the value will be 2.0 into 10 raised to 4 gram. Calculate the total mass of 3 samples that have masses 10.25 gram, 5.5654 gram, and 105.4 gram. So the total mass will be the sum of these. And in addition and subtraction, we consider the number of decimal places. And here this quantity has only one decimal place. So the answer also must be having only one decimal place. So the digit to be retained is 2. Digit to be dropped is 1. So therefore the answer should be 121.2 gram. The radius of a phosphorus atom is 1.10 angstrom. Express the radius in centimeter and picometer. So first we have to find out the unit factors. For that 1 angstrom is equal to 10 raised to minus 10 meter, and 1 meter is equal to 10 raised to 2 centimeter, and 1 picometer is equal to 10 raised to minus 12 meter. So the conversion factors are 1 angstrom equal 10 raised to minus 10 meter divided by 1 angstrom. So therefore 10 raised to minus 10 meter by 1 angstrom is 1. Then the second unit factor is this one. The third unit factor is 1 picometer by 10 raised to minus 12 meter. So the radius is 1.01 angstrom. And first we convert it into centimeter. So 1.10 angstrom into 10 raised to minus 10 meter by 1 angstrom. So angstrom cancels. Then we multiply this by centimeter. Meter and meter cancels, so it is converted to 1.1 into 10 raised to minus 8 centimeter. Now, we can convert it into picometer. That is 1.10 angstrom into this unit factor. It converts into meter. When multiplied by the third one, it is converted to picometer. So it will be 1.10 into 10 raised to 2 picometer. We can do it in different ways. This is only one of the way. Question number 4. A 47.5 ml sample of ethanol has a mass of 37.32 gram. What is the density of this sample of ethanol? Mass of ethanol is 37.32 gram. Volume of the sample is 47.5 ml. So density is mass by volume. So 37.32 gram by 47.5 ml. The answer is 0.7857, and the least precise value is 47.5. It contains 3 significant figures. Therefore, the answer should also contains 3 significant figures. So the last digit to be retained is 5, and a digit to be dropped is 7. So 5 increases by 1. So the final value will be 0.786 gram per ml. A small crystal of sucrose, that is table sugar, had a mass of 6.080 milligram. The dimensions of the box-like crystal, suppose the crystal is like a box, were 2.2 millimeter, 1.36 millimeter, and 1.3323 millimeter. What is the density of sucrose expressed in gram per centimeter cube? Mass is given. And first we have to consider the conversion factors. 1 gram is 1000 milligram, 1 centimeter is equal to 10 millimeter. So 1 gram by 1000 milligram is equal to 1, and 1 centimeter by 10 millimeter is equal to 1. And when you take the volume, 1 centimeter cube by 100 millimeter cube is equal to 1000 millimeter cube is equal to 1. Mass of the crystal is 6.080 milligram. We convert first into gram. So using this conversion factor, unit factor, and that is equal to 6.080 into 10 raised to minus 3 gram. Now volume of the crystal is that we multiply these quantities, 3.68016. So all the quantities has three significant figures. So we write this in three significant figures, that is 3.68 millimeter cube. Now 3.68 millimeter cube into this unit factor is converted to centimeter cube. That is 3.68 into 10 raised to minus 3 centimeter cube. Therefore, density is equal to mass is given in gram, volume is given in centimeter cube, that is 1.652. And here the number of significant figures is only 3. So therefore the answer must be in 3 significant figures, that is 1.65 gram per centimeter cube. Question 6. Two students ran the same reaction. One student obtained a 59.3% yield. The other student, using the different type of balance, obtained 55.638% yield. What is the average of their percentage yield? Write the answer in the correct number of significant figures. The average yield is sum of the yields divided by 2. And here we need consider the decimal place. We need not consider this one. So 57.469 is the answer. So here this quantity has only one decimal place. So the answer should be in one decimal place. The digit to be retained is 4 and a digit that is dropped is 6. So it increases by 1, 57.5%. And this quantity has three significant figures. This also is having three significant figures. Vinegar has a density of 1.0056 gram per centimeter cube. What is the mass of 3 liters of vinegar? 1 liter is equal to 1000 centimeter cube. So the conversion factor or the unit factor is 1000 centimeter cube by 1 liter is equal to 1. 3 liters into 1000 centimeter cube by 1 liter, that is 3000 centimeter cube. Mass is equal to volume into density. So 3000 centimeter cube into 1.0056 gram per centimeter cube. So that is 3016.8 gram. Now here there is only one significant figure. So the answer should be in one significant figure. So we write it in scientific notation, that is 3 into 10 raised to 3. The decimal place move 3 places towards the left. So it is 3 into 10 raised to 3 gram.
Thank you for watching and see you in the next video.